In the previous lesson, we looked at flow problems, and we also worked out the maximum flow in a digraph by looking at the minimum capacity. And most of digraphs in the flow problems, they are simple digraphs. Now we're considering what if we're given some more complex digraphs? Is there any easier way for us to work out the maximum flow? So today I'm going to introduce you cuts. We can use cuts to help us find the maximum flow in some more complex digraphs. It is difficult to determine the maximum flow by inspection for directed networks that involve many vertices and edges. We can simplify the search for maximum flow by searching for cuts within a digraph. So let's have a look. How do we find a cut in a digraph? This is an example shows a cut. Okay, as you can see, the cut completely blocks the flow of water from the source to the sink A. So to find a cut, we need to make sure we completely block the flow of water from source to the sink. Another example shows the cut completely block the source to the sink. Right. Okay. The last example, the dotted line on the graph above, okay, is not a cut because the material can still flow from the source to the sink from the top here. Now we understand how do we find a cut in a digraph. So we need to also understand how do we work out the capacity of a cut so we can use the capacity to find the maximum flow. Cut capacity is the sum of all the capacities of the edges that the cut passes through, taking into account the direction of flow. So two key elements we're looking at. One is the capacity of the edge, and then is the direction. The capacity of an edge is only counted if it flows from the source side to the sink side of the cut. Okay, this example shows the cut completely block the source to the sink. But when you look at the direction, the edge B to A is not counted because the flow of that edge is from the sink side to the source. So we only count this, the first and the last edge for our capacity. Now let's put it into practice. Calculate the capacity of 4 cuts shown in the network on the right. The source is vertex S and the sink is vertex T. Let's start with cut 1. Cut 1, it passes through 2 edges, SB and SF. As you can see, the direction both from source to the sink, so we're including both capacities. So 15 plus 20, the capacity of this cut is 35. Then cut 2, it passed through 3 edges, but for the second edge from F to B, it didn't really show the direction from the source to the sink. Therefore, we only count these 2 edges, 20 and 14. So capacity for cut 2, 34. Then for cut 3, it passed through 3 edges, BC, FC, and FD. And for the directions, they are all from source to the sink, so we're including all the capacities, give us 49. And the last cut, it passed through 3 edges, but DC has the direction from sink to source, therefore we only count FD and CT, which is 30. Now let's put everything together, cut capacity, and the minimum cut capacity. So a cut is an imaginary line across a directed graph that completely separates the source from the sink. The cut capacity is the sum of the capacities of the edges that are cut. Only edges that flow from the source to the sink side are included in a cut capacity calculation. The minimum cut capacity possible for a graph equals the maximum flow through the graph. Okay, so remember the last lesson we emphasized when we are looking at the maximum flow, we're actually searching for the minimum capacities. Right, second example, determine the maximum flow from source to sink. For the diagram shown on the right, so S is the source and the T is the sink. Now, if you want to pause the video and try see whether you can find all the cuts, okay, just pause the video and have a go. If you have tried, you should find a total of 6 cuts in this diagram. For these 6 cuts, again, we're going to work out the capacity. Okay, for cut 1, 19, cut 2, 14, 3, 22, then 12 for cut 4, 7, cut 5, cut 6 is 9. Right? Then when we're searching for maximum flow, we're actually looking for the minimum capacity. The minimum capacity for the cuts we have here is cut 5. Therefore, the maximum flow in this diagram is 7. Today we finish everything you need to know in flow problems. Make sure you revise what we have learned in part 1 of 15A as well.